The history of science is in very large measure the history of the unification of seemingly unrelated phenomenon. Isaac Newton saw the unity of motions in heavens and on earth. We had Thomson and Joule, who showed that heat is actually a form of energy. And then Ørsted and Faraday showed the connections between electricity and magnetism. What's more, each of these discoveries led to new, profound insights. The universal law of gravity, for example, the laws of thermodynamics, and James Clerk Maxwell's great principle that light is a form of electromagnetic radiation produced whenever an electric charge accelerates. This lecture is an exploration of the nature, the phenomenon of light. And I have three major objectives. First, I want to tell you in general about the nature of waves themselves, which transmit energy. Waves are characterized by four variables. We have the wavelength, the length of the wave itself. The frequency of the wave, how many times per second that wave beats. We have the velocity, or the speed of the wave as it travels through its medium. And finally, the amplitude, the height of the wave. Then I'm going to explore the three principal types of ways that light and matter interact with each other. We have transmission, when light passes right through an object. We have absorption, when light or the other energy is soaked up by a material. And finally, we have scattering, which is when light bounces off the surface of a material back out. And finally, I'm going to introduce the concept of the electromagnetic spectrum. In this lecture, I'm just going to focus on the lowest energy part of that spectrum, called radio waves. And then in the subsequent lectures, I'll look at the other parts of that spectrum, the higher energy parts, called microwaves, infrared radiation, visible light, ultraviolet, X-ray, and gamma ray. That's the next lecture. James Clerk Maxwell examined centuries of observations and experiments on electricity and magnetism. In particular, he looked at the work of Hans Christian Ørsted and Michael Faraday. He set down the behavior of these phenomena in a mathematical form. He used four equations, Maxwell's four great equations. The first was simply a restatement of Coulomb's law, and that's that there's a force that exists between any two charged objects. The second equation set down the basic characteristics of a magnetic field, in particular that every magnetic object has two poles, a north pole and a south pole, and that lines of magnetic force extend from one pole to the other. The third equation quantifies the relationship between an electric current and the magnetic field that's produced. Remember that a magnetic field is produced any time an electric current bends in a loop or around a curve. So Maxwell's third equation allows you to make some very important calculations, calculations that are vital to our modern society. If you're going to design an electric motor with a certain horsepower, this equation tells you how many loops of wire you need, how tightly wound, how much current has to flow through that electric motor. Remember, every circuit is a closed loop of wire. So it means that there has to be a curve in any electric circuit. And since electrons are moving around that curve, there's always a magnetic field associated with any electric circuit. Maxwell's third equation, it tells you how best to design that circuit so to minimize this effect of magnetic fields, especially if you want to get rid of it. For example, it's possible to design power lines with several wire strands that are twisted around each other in such a way that these little magnetic fields cancel each other out. So you minimize the magnetic field that might be the result of a high power line traveling overhead. And then you have the fourth equation of Maxwell, which states the exact relationship between a moving magnetic field and an electric current that's induced in a coil of wire. So you're creating electric currents by moving a magnetic field. Again, this is a really vital piece of information. If you want to design an electric power generator, you better know how strong a magnet you have to use, how many coils of wire you need, how fast you rotate those coils of wire, and so forth, because that's what produces the electric current. Maxwell's four equations, for the very first time, provided a complete description of electromagnetism. And it had a special bonus as well. But wait, there's more. The introduction of the concept of this electromagnetic wave. As we're going to see, this discovery has very profound consequences. But first, I want to explore the nature of waves themselves, because you have to understand how waves behave in order to understand the very special nature of the electromagnetic wave. I can't do the full derivation of how Maxwell showed that there were electromagnetic waves, but you can get a feeling for where this comes from. Let me show you a little demonstration, and you can think about how electromagnetic waves might be produced. Consider a single charged particle. And I can do that, for example, I can make my comb charge just by combing through my hair. So I comb the hair, you can hear little static clicks here. The comb now has a charge. Think about what happens if I wiggle this comb. There are electric charges that are moving back and forth in space. And these electric charges exert a force on every other electrically charged object in the universe, including every electron that's around, every electron everywhere, in the air, in solids, in your own body. It's happening even as I do this. The idea is that as the electrons in the comb move back and forth, they exert slightly varying forces on electrons in the air and other places, and these forces travel outward simply by the movement of charged particles that are affecting other charged particles all around. This is really just a consequence of Coulomb's law that says that every charged particle exerts a force on every other. Built into Maxwell's equations is this interaction, and Maxwell discovered that the information that one electron wiggles travels to other electrons at this speed of 186,000 miles per second. That's the speed of light. Now think about the effect of an electron wiggling back and forth. That motion, in effect, is a tiny varying electric current. And a varying electric current also has to produce a magnetic field. But a varying magnetic field has to produce an electric current. So the mere process of wiggling an electron with a charge on it creates a magnetic field that creates an electric field, creates a magnetic field, simultaneously back and forth, intertwined. And that's this electromagnetic radiation that radiates out in all directions. It's not just an electric field, it's not just a magnetic field, it's intertwined. And these are like waves of light that travel out from every charged object that wiggles. That's how you produce electromagnetic radiation. In order to understand more about the nature of light, I've got to tell you a little bit more about waves themselves. First, recall from the discussion of the first law of thermodynamics that waves provide a kind of energy. You can transfer energy from one place to another without moving mass. So a wave on the surface of the ocean, or a sound wave, my voice traveling to you, a seismic wave in the earth. You're not moving lots of mass, you're just moving the energy through mass. Waves always transmit energy through a medium. It could be solid, it could be liquid, it could be a gas. And for many decades, scientists assumed that light also had to travel through a medium, a massless medium they called the ether. We now realize that electromagnetic waves can travel through absolute vacuum. You don't have to resort to an ether. It's a strange concept, but that's what light does, and we just have to sort of accept that that's the way it behaves. In describing waves, we can use 4 different variables, and I want to demonstrate those 4 variables to you. I'm going to use a telephone cord, and you can reproduce this experiment at home, especially if you have a long telephone cord. Imagine yourself sitting there on hold waiting to talk, for example, to a government agency. You can practice your study of waves. We have 4 variables. The first is the wavelength. That's just the length from one crest to another. And you can see waves of different lengths by moving the cord at different speeds. So here's waves, for example, I'm making now maybe 1.5 feet long or so. You also have something called amplitude. If you don't put much energy into the cord, the amplitude is small. That's the height of the wave. But I can make the amplitude much larger just by putting more energy into it. A third variable is the frequency, and that's how many beats per second you have. You can have fairly low frequencies, or you can have quite high frequencies. The number of beats per second, and you can see how the number of beats per second also, in some cases, is related to the length of the wave. We'll see that's true for light as well. And finally, you have the speed of the wave, the velocity of the wave. You can demonstrate this just by flicking the cord and see the wave going back and forth. You just flick it, and back and forth it goes. And there's a speed moving along the cord. Those are the 4 variables of any wave. The length, the frequency, the velocity, and the amplitude. There's a simple equation that relates three of these variables. Wavelength, velocity, and frequency are related as follows. Velocity is equal to the wavelength times the frequency. In other words, velocity is in meters per second. That equals the length of each wave in meters times the number of waves that pass by each second. And we can do a simple calculation. For example, imagine that you have a wave that's 2 meters long and it travels at 6 meters per second. Well, you can apply this equation. Velocity equals wavelength times frequency. So if you want to solve, for example, the frequency equals velocity divided by the wavelength. In this case, we know the velocity is 6 meters per second. The wavelength is 2 meters. So the frequency then, 6 meters per second divided by 2 meters, 3 cycles per second. 3 waves per second pass by. And you can manipulate this equation any way you want to make this kind of calculation. These basic concepts are easily applied to electromagnetic waves. First, the only restriction placed by Maxwell's equation on the waves is that they travel at 186,000 miles per second in a vacuum. That's often referred to as the letter c. For example, in the famous Einstein equation, E equals mc squared. C is the speed of light, 186,000 miles per second. Also, by the way, about 300,000 kilometers per second, which is the appropriate unit to use when you're dealing with Einstein's equation. An important point about light is that shorter wavelengths, that is, higher frequencies, carry more energy per wave. And you can remind yourself of this: shorter wavelengths, higher energy, once again, by just resorting to a telephone cord. Long wavelengths don't require very much energy. But as you go to higher and higher energies, you get shorter waves. It's a lot more work to produce them, but that's how you remember it. More energy to make shorter waves. The highest energy electromagnetic radiation, therefore, has the shortest wavelength. There's no restriction on wavelength or on frequency. Note, however, that velocity for these waves is fixed. Wavelength and frequency then are dependent on each other. The wavelength is equal to the speed of light divided by frequency for electromagnetic waves. The frequency is equal to the speed of light divided by wavelength for electromagnetic waves. There's an inverse relationship here. Curiously, however, the only form of light known to Maxwell and his contemporaries was visible light. And visible light has a very narrow range of wavelengths, from about 15 to about 30 millionths of an inch. 15 millionths to 30 millionths of an inch is a very, very tiny range. Where were all the different kinds of waves? These were predicted by Maxwell, but nobody had seen them before. The situation is somewhat analogous to what a person would feel in a rowboat on the ocean. And I want you to imagine yourself in a rowboat on the ocean. The surface of the ocean can display many, many different wavelengths. You can have microscopic ripples, barely visible. You can have globe-spanning tides, waves that are essentially thousands of miles long. And you can have all sorts of waves in between. Now, the rowboat responds only to waves that are fairly close to the length of the rowboat. If you have waves that are 10 or 20 or 30 feet in wavelength, the rowboat's going to pitch and turn. You're going to feel those quite dramatically, and that's what you're going to be able to sense. But unless you were looking very closely at the surface of the ocean, you'd never see the tiny ripples. You wouldn't feel those, nor would you feel the tides. And this is very much like the situation with humans and the electromagnetic spectrum. Humans have only their eyes as detectors, and eyes can only see the visible range. So we never suspected the existence of many other wavelengths. And it was the discovery and the use of these different waves that have really transformed technology, particularly during the period 1880 to 1930, transformed society in many, many different ways because of the discovery of other forms of electromagnetic radiation. The only way for us to know about electromagnetic radiation is for it to interact with matter. So I want to take a few minutes to consider the various ways that light and matter interact with each other. It turns out that there are only 3 basic ways. They're called transmission, absorption, and scattering. And all 3 you experience all the time in your daily life. Transmission is when an electromagnetic wave passes right through an object. If an object is transparent, that's because the light passes through it. So window glass is transparent to visible light. Now, transmitted light can experience two important and related effects. First of all, the waves are often slightly bent. This is the phenomenon known as refraction. Refraction of light by a glass is the basis of all sorts of eyeglasses and optical devices. And you can see this phenomenon, of course, with the magnifying lens, that you bend light and therefore change the appearance of the object behind that lens. We also use telescopes and microscopes, very important sort of devices. In addition, whenever light is transmitted through a material, at least anything other than a vacuum, it slows down. This is a remarkable phenomenon. The amount of that slowdown is directly related to the amount of refraction, the amount of bending that you see with the lens. Diamond is one of the highest indices of refraction. Indeed, light slows down to a paltry 80,000 miles per second. That's less than half of its speed in a vacuum. So as soon as light hits diamond, it just puts on the brakes and creeps on through at 80,000 miles per second. The second way light interacts with matter is called absorption. Electromagnetic waves are a form of energy, and that energy can be transferred from one object to another, and it can be absorbed by materials, and that absorption is one of the processes that happens. When this happens, the light is often converted to heat energy. You've experienced this phenomenon if you've ever walked on a blacktop in the summer. Blacktop soaks up the sun's energy. It gets very, very hot, and if you put your feet on it, you really can burn yourself. That's why you often see people walking along the white lines of a parking lot in the middle of summer if they have bare feet. So any black material is basically absorbing the light. It's going to be much warmer in the wintertime, but it's also going to be much hotter in the summertime to wear black materials. And then we come to the third kind of interaction. That's called scattering. That's when electromagnetic waves bounce off a material and scatter off the surface. And this can happen in several different ways. You have diffuse scattering. Diffuse scattering is just what happens when light goes off a white surface and light rays come in and they bounce off in all directions equally. So the appearance of the surface is just white. You also have the phenomenon of reflection. And in reflection, you have a much more uniform kind of scattering. You find, in this case, that light bounces off quite regularly. Reflection off a mirror. And then you have a third kind of scattering called diffraction. Diffraction is a very special kind of scattering in which light waves are split up. You may have seen the kind of refraction effects you get off a CD, and you see that rainbow of colors. Light is being broken up into its component colors by this process. Iridescence is the process of diffraction. The conservation of energy requires that the energy of electromagnetic energy of radiation hitting a material has to be equal to the energy that's transmitted, absorbed, and scattered. So there's a conservation of energy here always. And often you'll see all three of these effects occurring simultaneously. For example, if you shine a light through colored water, you have some transmission, you have some scattering, and you have some absorption. All three processes are occurring simultaneously. The electromagnetic spectrum. I want to look at this electromagnetic spectrum because that's the continuum of all possible wavelengths, or equivalently, all possible frequencies of electromagnetic radiation. There are no natural sharp divisions in this spectrum. Every possible wavelength, every possible frequency can be produced. And there's really no natural divisions except from the human perspective that we see visible light and we don't see the others. So you might say, well, visible light should be categorized separately, and indeed it is. But from an intrinsic point of view, these are all the same kind of phenomenon, all electromagnetic radiation, all traveling 186,000 miles per second, all produced when electric charges or magnetic fields are accelerated, are wiggled in some way. It's convenient to divide the spectrum, though, into broad types of radiation, and we do that by three principal criteria. First, how the waves are generated, how we produce them in a technological sense, how they're detected, once again a technological question, and finally, how they're used. So these really are practical considerations. They're not scientific divisions. It has to do with sort of everyday things. Do we use radio waves? Do we use X-rays? And so forth. And you'll see how that comes into play. There are a bunch of common divisions of this electromagnetic spectrum. They are radio waves, microwaves, infrared, or heat radiation sometimes it's called, then visible light, then ultraviolet, X-ray, and gamma ray. This list is in the order of increasing energy, also of decreasing wavelengths. Remember, the shorter the wavelength, the higher the energy. That's an important concept. For the remainder of this lecture and all of the next lecture, I'm going to explore these different wavelengths of the electromagnetic spectrum. Waves that travel 186,000 miles per second, waves that are produced by accelerating electric charges. They are so important in our everyday life. They're used in so many different ways. It's a key element of scientific literacy, and I want to share with you these different ideas. In this lecture, I'm going to begin the survey by looking at the longest wavelength, the radio waves. Radio waves were the very first of the invisible kinds of electromagnetic radiation to be discovered. They exemplify the behavior of electromagnetic radiation. Radio waves were discovered by the German physicist Heinrich Rudolf Hertz, and this was in a series of experiments in the late 1880s. Hertz was born in Hamburg, Germany. He was born in 1857. He studied physics at the University of Berlin, and he spent much of his career teaching at the University of Bonn. He died in Bonn in 1894. So he was a 19th century scientist. He was born and raised and studied in the heyday of the discoveries of the electromagnetic spectrum. And he made this very, very important discovery of radio waves. He'd read Maxwell's papers. He was determined to observe these predicted invisible kinds of radiation. He set up a series of experiments to do just that. From 1886 to 1889, he generated an electromagnetic field in one part of his laboratory, and then he measured the strength of that electromagnetic field in a different part of the same laboratory. What he did was this. He hung large plates of zinc metal at various points in the laboratory, and as he moved those zinc plates around, he saw the shifting of the field. He saw different concentrations of this invisible energy, and he was able to prove to himself that the different shifts corresponded to reflection of energy off the plates or absorption off the plates, and therefore this was a kind of wave-like energy, and he was able to measure the wavelengths and some of the other characteristics of these invisible waves. By the way, the unit of frequency is called the hertz. A hertz is 1 cycle per second, and it's named in his honor. So when you look at your radio dial, you may see kilohertz or megahertz. That's named after this great German scientist. Shortly after Hertz's research, the practical use of communication by radio was demonstrated by the Italian inventor Guglielmo Marconi. Marconi was born in 1874 in Bologna. And that's where his businessman father owned a large estate. He was quite wealthy. He was educated at home and in schools in Italy and in Britain. He never pursued a college career, nor did he need to, because he had all the benefits of that family wealth. His seminal experiments were conducted in a large attic on the grounds of his Italian home. Can you imagine having an attic laboratory, an attic large enough to conduct major scientific experiments? Well, that was Marconi for you. He generated radio waves with a primitive spark device, just making electric sparks, and those created radio waves. And then he used a telegraph to produce short bursts like this. So this was actually using a telegraph-like device. Much of his success was because he designed and improved antennas. He was the first one, for example, to take an antenna, put it in a vertical configuration, and ground it so that you had much better reception characteristics. Gradually, he was able to increase the transmission and reception of these radio waves from a mile to 10 miles, eventually to 100 miles in the year 1896. And these were just short bursts of radio pulses like Morse code. Marconi established the first transatlantic wireless communication in 1908, and he won the Nobel Prize for Physics in 1909. After that, he became a wealthy man with a flamboyant lifestyle. He's said to have taken more than 100 transatlantic ocean voyages. He's also said to have engaged in a great number of shipboard romances, wooing and promising marriage to any number of rich young women, and he did actually end up marrying one of these eventually. Apparently, it was a very happy marriage, too. Radio waves, we now know, they include electromagnetic radiation with wavelengths between about a foot up to several miles long, the lowest energy part of the electromagnetic spectrum, the longest wavelengths. The frequency of these waves is measured in thousands or millions of cycles per second. That's kilohertz, or megahertz. Radio waves, like all the electromagnetic waves, are produced when charged particles move back and forth and oscillating. The tall antennas that you see near many radio stations, they're metal structures in which a large number of electrons actually are moving back and forth. They're actually oscillating back and forth, thus producing the strong radio signals that you detect. Radio waves are ideal for communication because they travel through the atmosphere. They travel through building materials. The shorter wavelength radios, such as what we call FM broadcast waves, are not easily scattered. They require some sort of line of sight to the radio tower, so normally you can't get an FM radio station more than about 40 or 50 miles from its source. But under the right conditions, the longer wavelengths, the AM radio broadcasts, actually can curve, bounce off the atmosphere, scatter, and therefore travel for many hundreds of miles, even beyond the horizon. Information is commonly conveyed with a radio signal in two different ways, two contrasting ways. All radio broadcasts start with what's called a carrier signal, which you tune your radio, and a flashlight, this shining flashlight, can be thought of as a carrier wave in this sense. And you can do two different things. You can change the amplitude of the wave, and that would be, in the simplest case, just turning the flashlight on and off, and you could send Morse code in various ways by turning a flashlight off for short and long pulses. That's analogous to amplitude modulation, where you're changing the intensity of the wave. But you can also use frequency modulation, or FM broadcast, and that's nothing more than changing the wavelength of the wave slightly. And we'll see that's analogous to having two different colors, and if you go from one color to another in a repeating pattern, you're conveying information too. That's analogous to an FM, or frequency modulated broadcast. Because radio waves radiate out in so many different directions and over such great distances, society needs to regulate who uses which wavelength, or which band of radio, as it were. That's why we have the International Telecommunications Union. That's an agency of the United Nations. And also in the United States, the Federal Communication Commission, that's the FCC. These control what is called electromagnetic real estate, because each wavelength is a kind of valuable commodity over which you can convey information. Specific radio bands are allocated to, for example, amateur radio operators, for police, for emergency vehicles, for navigation, for space communication, very important to have a separate band for that, and so forth. In addition, there are a few specific wavelengths that have been set aside as standard frequencies, and they broadcast on that frequency all the time, and you can use your radio receivers to pick up those specific frequencies and make sure that your equipment is working properly. Radio astronomers use large dish-like antennas to detect radio waves that are coming from distant objects, stars and galaxies that are far, far away. These stars and galaxies have swirling clouds of charged particles, and so many objects in space emit radio waves because they're accelerating charged particles. Those waves travel 186,000 miles per second through space, sometimes for hundreds of millions of years, and they're picked up by radio telescopes. As we'll see in Lecture 60, you can also use radio waves as a way to possibly detect the existence of intelligent life elsewhere in the universe, because if you wanted to communicate from one planet, from one star to another, that's the way you do it. Let me summarize this lecture. Maxwell's equations point to the existence of all different kinds of electromagnetic waves. That's energy that travels 186,000 miles per second, energy that's produced through the acceleration of electric charges. These waves differ in their wavelengths and in their frequencies in an inverse proportion. Electromagnetic waves can interact with matter in three different ways. They can be transmitted right on through transparent materials. They can be absorbed, soaked up, or they can be scattered by the processes of diffuse scattering or reflection or diffraction. Radio waves are the very first source of invisible electromagnetic radiation to be discovered. And in the next lecture, we're going to continue on this journey through the electromagnetic spectrum and look at all the other different kinds of electromagnetic radiation.